All right, recording is rolling. Tuesday, October 10th. I got a demo for you guys. There are turntables on your desk, but I'll tell you guys more about that in a minute. Our main thing today is I want to knock out as many chapter 7 puzzles as we can. So I'm going to give you guys a bunch of notes today. We're going to solve a bunch of physics puzzles. All right, reminder, first 9 weeks is going to end in like I think a day or two here. All right, so check focus for all your classes. Make sure you've turned everything in. All right, and then tomorrow we'll start universal gravitation. We'll combine that with all this rotation stuff, make orbits. So we're going to, right. So did I think recently one of the puzzles that I've been throwing at you guys, like some version of this, right? Like a car going around a big curve. Okay. Now, if AP asked a question like this, they probably wouldn't have you solve for like what is this bank angle, but I mean, like some of you guys are gonna be engineers one day. It might be good to be able to do that, right? Their question would probably be more conceptual, like what force is acting as the net force? And then you would say, oh, well, it's the horizontal component of the normal force. Actually, I've seen them ask that exact question before. So that's kind of about as deep as they would go. Okay? But here, I do want you guys to see this in motion. So let's flip over here. All right, and here we go. All right. Ooh, look at that real steep bank wall right there. This motorcycle's going around. So motorcycles, right? Now, down the bottom, you guys see a couple cars. Right? Do you guys think those cars are way more massive than those motorcycles? Okay. So if those cars are driving the wall, then are those cars going to have to go faster, slower, the same speed as those motorcycles? Well, I think we're about fine. I think we're about fine. Hey, I guess here, if those motorcycles were going a little bit faster, they tend to drift up the wall. If they were going a little bit slower, they kind of tend to drift down the wall. You guys can imagine that, right? And the radial size wouldn't change a whole lot because the wall is just so steep. And our time. Who's going faster, the car or the motorcycle? Are they going the same speed about? They're going about the same speed? Huh. So yeah, about the same speed to maintain about the same spot on the wall, or you could say maintain about a constant radial size. So it's looking like the mass is going to kind of cancel out, right? Somewhere in one line. Right? If you go to engineering school, they might call this dynamic equilibrium. Now, guys, are those motorcycles, those cars, are they in true static equilibrium? No, because they're on a curved path, right? They might have a constant speed, like there might be a speedometer needle that's not actually changing, right? The radial size doesn't change and the speed's not changing, but the direction's changing. They're on a curved path. There is a net force, right? Something to do with the normal force on the wall, right? You might call that dynamic equilibrium, where the radial size doesn't change and the speed's not changing. Right? Similar idea with the Earth orbiting the moon, or so the moon orbiting the Earth. That's not static equilibrium, but you might call it dynamic equilibrium, right? So, so they're all going about the same speed. So it looks like mass cancels out somewhere in the equation. But let's go check this poster. Hey, mass does cancel out. Remember that? Remember the setup was, all right, so this vertical component of the normal force balances the weight. This horizontal component is the net force, which therefore would be mv squared over r. Right? And we have two legs of a triangle. That's a tangent relationship. So take mg multiplied by tan of that angle theta, which is the same side. That'll spit out the opposite leg. There you go. Mg tan theta is mv squared over r. Rearrange it. But mass cancels out. Yeah, so the mass. Next thing. You guys do see some turntables. I was gonna do a lab with you guys. I think what I'm gonna do with this lab instead is just preview with you guys real fast, and then probably in spring we'll have this as a review because we'll probably need at least a couple labs in the spring. So what if I get this Roosevelt on this turntable? Actually, let's get a few on here, right? And I give this thing a spin. Right? Do you guys think if I spin this too fast that these Roosevelts are gonna start sliding off? Yeah. Which one? Are they all going to slide off at the same time, or is one of them going to slide off first? What do you think? One outside. Oh, you think one on the outside slide off first? Let's see. Oh, it does. And then that guy, and then this guy is real hard to get off. He's just so close to the center. Okay. Okay, so that might. Do you guys think that sliding off has something to do with the coefficient of friction? Right? Yeah. That maybe if it breaks the coefficient of static friction first, then it would slide off at some point, right? Huh. Hey, do you guys think if you knew, say it's radial distance from the center, right? You guys got really center dust. So like how far out is it? so many centimeters. There's about 10 centimeters right there, 10 centimeters radius, right? And you knew how fast it was rotating, which is what's the physics term for that? How fast it's rotating? Angular velocity, angular velocity, right? Yeah. Sometimes you hear rotational velocity, angular velocity, right? If you knew that, you could quantify that in radians per second, right? Do you think you could calculate what is the coefficient of static friction between those two surfaces, right? In principle, right? Let me show you guys how you would do it, right? And then, I mean, if you remember by spring, then that's amazing memory, and that would be super awesome. And if you don't, then hopefully you can figure it out by then, because you'll have the critical thinking skills to be able to put this back together. Okay? So I'm thinking, zoom in a bit here. Okay? So here's my turntable from the side. Oh, it's got some angular velocity, radians per second. Here's the Roosevelt right here. It's got 3 forces on it while this is in motion. 3 forces: a weight down, a normal force up, which are balancing each other out pretty well. And then the friction force is acting as the centripetal force. Is it? So when I'm setting up this proof here, that's my very first step. I'm saying the centripetal force is providing centripetal. Sorry, the friction force is providing centripetal force. Guys, what's the formula for friction force that you guys know? What times what? Coefficient of friction times normal force. Yeah, right? Right? So some material property that you can be solving for is times normal, right? Now, if the two surfaces are sliding past each other, that'd be kinetic friction. Notice I've said this is equal to this, right? If we're talking about coefficient of static friction, we're talking about the point that the coin actually starts sliding, right? So it breaks the static friction. So we're like maxing out the static friction. So I could throw a subscript S here, but this is the point that it breaks the friction and starts sliding out, right? What's the formula you guys know for centripetal force? You guys know 2. One of them is mv squared over r. What's the other one in terms of this angular velocity? M omega squared times. Do you guys see one up here that says O'Neill cylinder? A poster hanging above me, it says O'Neill cylinder. Does it say right there? M omega squared times r. Right? All right. Oh, guys, what can I substitute for normal force? Mg. Yeah, mg. Right. That's the next step. Okay. Oh, hey guys, what cancels out on both sides? Mass. So if you replaced one coin with a different coin, or the different math, maybe it wouldn't matter as long as the materials were the same, because that's something to do, right? The materials are the same, the mass doesn't matter, right? Or maybe you stack a lot of weight on top of the coin, right? And if your goal was to figure out what's the static friction, let's say, would you know everything else? You could measure R with a ruler. You'd be allowed to know what G was, and I bet you could use a stopwatch and figure out somehow how fast it was rotating, right? So there's enough info there you could find that. Right. So that's why I'm having my honors classes do. You guys, I think I'm going to save this for the spring, and then we'll do it then. Okay. Right. But you guys could probably figure that out in the spring. Right. We're going to find out in a few months. All right. Textbook puzzles. Ooh, this is I don't know about you guys, this is always my favorite part of physics, just sitting down and just solving these. So yeah, say that. And I know this class we've done like a bunch of labs, a bunch of lab time, but yeah. All right, number 16. 16. It has been suggested that rotating cylinders, so many miles long, so many miles in diameter. Oh, they're giving us these American units. Be placed in space and used as colonies. Ooh, I think I was calling that O'Neill cylinder. I got somewhere off the internet. What angular speed? Angular speed. Look at there. All right, omega. Should a cylinder have so that the centripetal acceleration on the surface, so they're talking about the inside surface walking around, right, equals the free fall acceleration on Earth? Oh, I think we did almost this exact question yesterday, didn't we? Right? Was this like the starter question that somewhere we incorporated? Right? But they're talking about this, aren't they? Talking about this, right? Cylinder, it's rotating, right? Now they didn't exactly say, but they're implying it's rotating about the central axis here, right? So you can like walk around on the inside, right? Oh. There is here. There's a little detail I want to mention. So number 16. They talk about it being like 10 miles long and 5 miles in diameter. If I actually draw that, that looks something kind of like that, right? And then where the length is twice the diameter, that's kind of what they're getting at, right? There is technically a problem with that. There will never be an O'Neill cylinder that's shaped that way. Do you guys know why? Right? It's a really obscure corner of physics. Something called the here. I'll write this down. Intermediate axis theorem. Maybe I should have capitalized that or something. I don't know, right? But there are certain axes that it could orbit about stably, and this is not one of them. So if people are like starting to walk around on the inside, you have tiny shifts in center mass, right? That would be plenty enough to eventually this thing's kind of like flip and rotate about a different axis, which wouldn't be any good, right? But if you have a cylinder that looks more like the one in the poster I made for you guys, where it's like this, right? It rotates about this axis, right? This actually would be a stable rotation, so that could be, right? So ignore the whole like 10 miles on thing. Right? Let me show you guys. You can actually prove this with your cell phone, right? So think about your cell phone, right? So how could you like rotate this? Could it rotate about this axis like this? Right? If you throw your cell phone like this and like rotate it, like it could set up a stable orbit about that axis, right? Right. So it's a little tiny with right. What if you rotate about like around about this axis right here? Did you do that? Right. Oh yeah, it'll do that, no problem, right? But you know what you can't do? You know what you can't do? I guarantee you cannot do this, right? I bet you cannot make a clean rotation about this axis right here. If you flip your cell phone like this, right? No way does it ever do that, right? It will always like make some like weird like turn in midair like that, right? Yeah, I guarantee you can't do it. You can't do this, right? And that's because of this right here. Right? Anyway, that's a side note. That's kind of a deep corner of physics.
What if you tied it around a string and went on chain?
Oh, okay. If you tied it around a string, yeah, but not just okay. All right, you got me. You got me. Yeah, but yeah, but just like flying through the air. All right. Anyway, let's go with 5 miles diameter is really the number we care about, right? So how fast does this thing have to rotate? So they went with diameter. They will use D for diameter is 5 miles, right? So how fast does this thing have to rotate? We'll call that omega, right? I guess I need to give you guys some kind of conversion, right? So like if you want an exact conversion, the conversion for distance is 1 inch is defined as exactly 2.54 centimeters, right? Let's use one that's a little bit faster, right? Let's say that 1 mile, here, 1 mile is approximately 1.61 kilometers, I think it is. Okay, let me double check that. I'll Google that. While you guys are solving that, I'm going to do a Google check on myself. All right, I think that's the conversion. It's really close to the golden ratio, which is about that is 1 mile to kilometer. Yeah. Let's go with what I wrote up there. It's like 1.60934 something. Okay. All right. So you guys are solving that, right? In fact, if you look at your notes from yesterday, we looked pretty well solved this yesterday. I could probably help you out. How fast does that thing have to rotate? And so everyone walking around on the inside here feels like they're in Earth gravity. Right, so I'm giving you guys a head start. You guys are solving that, right?
What exactly are you talking about? Is that 5 miles or 50?
5 miles, 5.0. Did you guys ever in school learn about Fibonacci sequence? Did you guys learn that Fibonacci sequence? No? Okay, yeah. So some of you guys, all right. If you ever did, all right, so the numbers go like you just take two numbers like 1 and 1 and add them together and get the next number. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8. It goes like 13, 21, stuff, right? If you take the ratio into those, it ends up being the golden ratio. The golden ratio, like weirdly enough, just by coincidence, ends up being extremely close to the ratio of a mile to kilometer. Okay. So look, two numbers of golden ratio, 5 and 8, 8 kilometers, 5 miles, they're about. So okay. Anyway, so there's step one. Right, so but you guys are ahead of that now, right? Right, you guys are on to the next step. Right, I'm trying to give you guys a head start so you guys can beat me to the answer. You guys beat me to the answer?
Yeah, I already got that.
Right, so that's the diameter. All right, I'm gonna go ahead and finish this out, but I hope you guys are beating me to the answer. So centripetal acceleration is omega squared r. Therefore, omega squared is this. Therefore, omega is this. All right. Here's the answer in terms of variables. I'll plug in some numbers. Half of that diameter would be the radius, wouldn't it? Half that diameter is the radius. The 40, 25 meters. Thereabouts. Radians per second. Oh, I should have asked you guys what the unit was going to be. You guys would have said radians per second because we're talking about an angular velocity, right? That's how fast it's rotating. Right? Okay. Ooh, I got my own follow-up question. How much time would it take to go around once? How much time? All right, I got the answer on my calculator screen. How long? I think longer than that. What you got? All right, I got what Gavin got. Yeah, about 128 seconds. So what was that, like over 2 minutes about? Yeah. Right. So here, I got some space right here. I can do this. Okay. So 1 revolution, right? And I'm going to convert that into time, right? Into time. Okay. I know that 1 revolution is equal to how many radians? 2 pi radians. And every every 0.049 radians, it's like 1 second. Yeah, it should give you, what was it, 128 seconds, I think, something like that. Okay. And then, was that right? Yeah. Or alternatively, you could have said something like this: distance equals speed times time. You could have solved time that way. The distance divided by speed, right? Either way you do it. Okay. All right. Next one. Number 18. Okay, so we're done with. Guess we're done with the O'Neill cylinder for now, right? Okay. Right, number 18. And
what did you get?
Okay. Okay. So number 16. Okay. So centripetal acceleration is omega squared times r. Right. You divide down the r, take the square root, that'll give you omega. Right. So angular velocity. Right. You just pop in the numbers. Right. So there's the target angular acceleration, right, so that you feel like you're in Earth gravity. Right. That's centripetal acceleration. And right, there's the radius, it's half the diameter. Right. So like that many radians per second. Right. Oh, yeah. Right. So they said the diameter was 5 miles, 5 miles diameter. Right. So okay, you have to convert everything to metric units. Right. Now, why would I want it to be metric? Because I know the gravity field in metric units, meters per second squared. Okay. So I need the diameter in meters. So they gave the diameter in miles. I know that every 1 mile is 1.61 kilometers. Right. Okay. So it can convert that way, right? And then 1 kilometer is 1,000 meters. Okay? So the diameter is like 8,000 some meters. therefore the radius is half of that. It's about 4,000 some meters. Okay. All right, number 18. An adventurous archaeologist who has mass of so many kilograms tries to cross a river by swinging from a vine. Ooh, swinging on a vine. The vine is so many meters long. Its speed at the bottom of the swing is so many meters per second. Okay. The archaeologist knows that the vine has a breaking strength of 1,000 newtons. Ooh, right. So if he's pulling on the vine with more than 1,000 newtons, it's going to break. If it's like 900 newtons, it's going to be safe. Right? Does he make it across the river without falling in? So 18. Okay. I'm gonna change some numbers here. Okay. I'm gonna give the mass of my archaeologist, let's call him 70 kilograms. It's a little bit different from the book. I'm gonna have the vine length as about 9 meters long. And let's say the speed at the bottom is okay, they said 8 meters per second. I'll go like how about 12 meters per second, right? Okay. And let's say the breaking tension, so tension max, so that's the tension force maximum. Right? They said 1,000 newtons. Maybe I'll go. Let's see. I'm gonna go 900 newtons. Okay. Okay. So I have a different scenario. Right? Maybe the book either breaks or doesn't break, and mine does the opposite. Possibly, I don't know. Right? I mean, you guys have the solution somewhere out there. Right? So, right. So let's get a picture what's going on. But there's this guy, say, swinging on a vine. Right. Here we go. Here's our archaeologist. Oh, hat. Swing down. There's some speed at the bottom here. Speed at the bottom, right? Which they did give to you, right? They gave you the speed at the bottom, right? Right now, a few weeks from now, we're gonna actually take this exact question, and there's gonna be an extension on this. So I just want to plant an idea in your minds right now. What if you know the length of this vine? Okay, which you did. What if you also knew the starting angle? Which notice they did not give you here, right? They didn't tell you what the starting angle was, right? And maybe he starts from rest, or maybe he pushes off, right? If you want to like give him a starting speed up there, maybe not. Okay. He's gonna go through some height change. You guys see how there's like a change in height here? Right. Now this is all extra, but I'm just planting an idea for the future in this class.
Mr. Griffin?
Yeah.
Would the bottom speed be like the fastest speed too?
Yeah, true, right? Because here he'd be going maybe 0 or slow, right? He's going faster. That would just be his maximum speed at the bottom. And then after he passes that point, doesn't he slow down, right? Right. So there's like a pendulum type motion there, isn't there? Right? Do you guys think in principle you could, like if you knew the starting angle and the length, you could calculate the speed at the bottom? Could you do that? Right. Let me give you guys a kind of a shortcut way that actually does work. There's kind of a way you could figure it out. If you can figure out what this height change is based on geometry, you guys think you could, if you knew this length and the starting angle, you guys think you could think, oh, well, I learned a geometry class. You can figure out this here, something with the cosine, you could do subtraction, you could figure out what that delta H is, the change in height, right? That change in height, think of it. Do you guys think if Galileo dropped a ball and it dropped some height, maybe going some speed at the bottom, and that would match maybe like how fast it's going, like swinging down? It turns out it does. We'll show that in a few weeks, right? You can technically use this third kinematic equation, and for the height change, you can call that x and put him in a gravity field. And okay, if he kicks off, you have initial velocity. If he starts from rest, you just call this 0. You can figure out the speed there, right? It would work out like square root 2gh kind of deal, right? So yeah, I just want to plant that idea because when we do conservation of energy, we'll do this like a different way, and it'll work out to also stay. Right? Anyway, let's say we've already solved that, right? And we've already figured out he's going so many meters per second at the bottom, right? And now the next thing we got to figure out is because the tension in that vine, is it so much that it's going to break or not? Right? Is it going to surpass this number or not? Right? Let's do a free body diagram. I'm going to break out a different color ink here. Let's break out the pink ink. It's free body diagram. And the fact that he's in motion does matter. Because if he wasn't in motion, if he was just hanging there, he'd have a weight down. So I'll call it like mg, his weight down. Right? And what would the tension be compared to his weight if he's at rest? Would it be the same? Right? Yeah, it would just be the same, right? Weight down, tension up, right? But the fact that he's in motion, is that still true? What do you guys think the tension is compared to his weight, the fact that he's in motion? Think it's more? F sub t, right? You guys see that how that is larger than that? You guys see that? Okay. So maybe we could say it this way: the tension force, the magnitude of that is greater than the magnitude of his weight. Right? So absolute value bar is like magnitude, right? Right? Because he's in motion, right? In fact, if you take the difference between those two, what kind of force does that net force represent? Starts with the C. Centripetal. Because hey, he's on a circular path, isn't he? He's on a curved circular path. I mean, this would continue if he keeps swinging. Okay? Like that pendulum right there, that's a circular path. Okay? So what's that? Maybe I could say the difference between those two. So the tension force up. Right. All right. So here's your given values, something like that. Maybe we could say the tension up minus his weight down. That's the net force, right? Right. That is what's providing the centripetal force, right? Isn't that like the foundational premise behind this whole setup? And after that, you just do some substitution, some algebra, and eventually we're going to solve for the tension force. Right? I mean, that's our goal. And we're going to compare it to the maximum tension. Okay? You guys get that? Okay. If you can get this set up and you know some algebra, you're good to go. Right? Let's put out the rest of this. So the tension force we're solving for minus his weight. So that difference is the net force. What should I substitute for centripetal force? What expression should I write right here? Yeah, mv squared over r, right? There you go. mv squared over r. Right. I like that one for a couple of reasons. One I like is because it's like a point mass on a string. I mean, rather than using m omega squared r, it's not like a turning turntable, right? It's like point on a string. Also, the fact that we know what his speed is at the bottom, right? Because maybe we figured that out by this point, or the book gave it to us. Okay. Oh, so if you're solving for tension, maybe solve in terms of variables. Isn't the tension force just going to be his weight plus the centripetal effect? Is kind of how you could think of it, right? Or from his frame of reference, it's like if he closes his eyes, doesn't he think there's a huge? Does he feel really heavy or really light at this point? Feels extremely heavy. If he closes his eyes or he's blindfolded, he thinks there's extra gravity. Oh, that's kind of what this says here, right? So the tension pulling him back, it's kind of like his usual weight plus this centripetal effect, sort of, right? He thinks there's a centrifugal force pushing him down, but there isn't, right? There's a centripetal force because the tension is more than his weight that's pulling him up. So here's the answer in terms of variables. Right? I guess I could change these given values to whatever, and this could be like the universal solution. Right? If you like, you could factor out his mass, and you could do stuff with that. That's fun too, right? At some point, we need to plug stuff in. So let's plug some numbers in. So the tension force is going to be this guy is so many kilograms. I'll call Earth gravity 10 meters per second squared. Right, here's 70 kilograms again. We figured out, or the book told us, 12 meters per second is going to, don't forget to square that speed. And then divide by, guys, what should I do for radius to curvature? What is the radius? Yeah, 9 meters, because it's the same thing as the length of the pendulum, isn't it? You guys see it's the same thing? Then just pop that right there. So many meters, length of the pendulum is, the length of the vine is the radius, right? All right, let's go that plus that times that squared on that. Okay, that's 9.0 right there. So I'm getting this many newtons, that many newtons right there. Right. So with the numbers that I've set up, is it going to make it safely cross, or is it going to break at some point? Yeah, because that is exactly, it will break, right? Because that is greater than T max, or it's just that F sub T max. That's what I meant to do. I'm trying to reserve capital T for time period. Okay, so F sub T max, which was 900 newtons, right? Because I could have made that number 1500 newtons and still would have broken. Right? Right? You guys got that? And you guys could figure that out. If,
plug in the values from the page, and he also falls.
all right. Yeah, I couldn't remember if you did or not, but all right. Number 20. A coin rests on a 15 centimeters from the center of a turntable. Hey, coin on a turntable, coefficient of static friction. That sounds kind of like what's on your desk right now, right? You guys got coins on turntables, give it a spin. Right? Now, this time they told you what the coefficient of friction is. They said it's like 0.35. I'm having my students solve for that, and that's the solution, right? So maybe kind of backwards this, right? The turntable starts from rest at time 0 and rotates with a constant angular acceleration of so many radians per second squared. Ooh, once the turntable starts to rotate, what force causes the centripetal acceleration? So let's answer that first, guys. What forces cause the centripetal acceleration? What allows it to stay on a curved path? Friction. Yeah, friction, right? Because we're talking about, bam, that guy right there. Isn't this friction force allowing this going to stay on this curved path right here? Right, friction. Right. Of course, you need some other forces to also allow it to happen. But right? The friction force is centripetal force. Right? Under what condition does the coin begin to move relative to the turntable? Right. So, what do you guys say that when it breaks static friction? Right. Something like that. And after what period of time does the coin slip? You know what this makes me think of? I think you have to combine a bunch of parts of physics, right? So there's some kind of rotation going on. We're looking for maybe what's the angular velocity so that the necessary friction force like maxes out the centripetal force, kind of, right? And then we're gonna have to kick back to kinematic motion. They talk about like starting from rest, accelerating at this value. When it gets up to such angular velocity, like how much time would that be? That sounds kinematic, doesn't it? Right? So we're gonna have to put different parts of physics together. Ooh, this sounds kind of complex, but kind of fun. So, notice they did not tell you the mass of the coin, but I think the mass of the coin cancels out anyway. So let's see, number 20. I'm gonna change some values. All right, so turntable. Let's get this central axis that's rotating about omega. Okay. I'm gonna have my coin a different distance from the center. Let's put this down here. Let's say R equals, how about 0.22 meters? How about that? Is that 22 centimeters, 0.22 meters? Okay. And I'm going to have here, let me draw a free body diagram. Can you guys draw the free body diagram as I do it? It's got a weight. It's got a normal force. And also, what kind of force is it spinning? But what force is acting as a centripetal force? Friction. Yeah, friction. So I'll label it F sub FR. Guys, do you ever on a free body diagram want to label a force just centripetal force? Do you ever want to do that? No, right? So the centripetal force is either a force, like in this case, it is the friction force, it's provided by a force, or it might be a combination of forces. Like the guy swinging on the vine, it was the difference between the tension up and his weight down, right? There's always some conventional forces acting as the centripetal. Right? So they gave you coefficient of static friction. I'm going to make up a different number. Let's say minus like 0.50 is what I'm going to have. Right? And they also gave you an angular acceleration. I'm going to make up something different. Maybe in mine's like 1.1 radians per second squared. Okay. They told you omega naught was 0, so I'll just go ahead and keep that radians per second. Starts from rest. Okay. So here's your given values. Also, that radius is a given value. Okay. Of course, I bet if you can solve this in terms of variables, then you'll have a general solution anyway. So maybe try that. See, I'd really like to know what angular velocity that it slips. So maybe I'll say something like this. The centripetal force is provided by the friction force, right? Now, in my setup here, I reverse those. I put friction is provided by centripetal. Here I'm saying centripetal provided by friction. Why am I doing that? Because what I'm solving for, I just want to show up on the left side because it just looks cleaner, I guess, right? Here, what I'm solving for shows up on the left side, right? I'm just thinking ahead a few steps. Right? Centripetal. All right, guys, what do I want to substitute for centripetal force? What expression right here? I don't want to write, do I want to write mv squared over r? Or is there a better way? Turntable, right? Yeah, m omega squared times r, right? If you do mv squared over r, you can do a little substitution and you'll end up with this anyway, right? So the turntables use something with angular velocity. Anyway, we have to figure out angular velocity anyway, so we may as well, right, have some version of that. Okay. And what do I want for friction force? Coefficient of friction times the normal force. Wouldn't that be? And I'll go static friction because we're trying to max out static friction. So I can say equals if it's at the point that it breaks the friction and starts sliding. Okay. Otherwise, I'd have to set up an inequality. Right. So let's do another substitution. M omega I'm solving for squared r is equal to this normal force. I can substitute what? mg. Yeah, because this is equivalent to that. Because some of the forces in the y direction goes to 0. Right, that's why I can make that substitution. Right, here's what cancels out on both sides. Mass of the coin, right, which they never gave you. Right, so if they don't give you a quantity, that's probably a hint that it does end up canceling out. Maybe you should look for that, right? Or if that's really confusing, you could just make something up, right? You could just plug in whatever mass, right? You just cancel out anyway. Right? Did you guys see 2 algebra steps away from just solving the universal answer here? Right. Divide by r, take the square root. So 2 steps later, it looks like this. Omega equals the square root of mu times g, all divided by r. Right? Actually, that's not exactly what they asked. They asked what time period. Okay, so that's like the first half. That's the first half of this problem. So now you guys got an answer for that, right?
It says one turntable to rotate with force causing the centrifugal acceleration. The point is
Okay. All right. So back to the first question, guys. While the coin is on the turntable, and it's just in a circular path.
Friction.
Yeah, friction. Yeah, friction is causing the centripetal force. Right. That was the setup here.
The interruption, we're helping investigate this step. That's 1, 2, 3.
Oh, all right. I guess it does work for us now. All right. Send me an email later. Okay. So yeah. So the fact that the friction force was providing the centripetal force, then we made a bunch of substitutions, and we got what is the angular speed where it would break the friction is what we've just found out, right? Like it would have to rotate this fast. Okay. And then you can take all your given values, you can just pop them in and get something, right? Okay, so right. That's the first half of this question. The second half of this question is to say, well, how much time would it take to spin up to that point? Because there's something about angular acceleration. So can we switch over to kinematic motion? All right, let's do a checklist here. Let's do a tax VV checklist. Time, acceleration, displacement, initial velocity, final velocity. Of course, these are all the angular equivalents, right? Okay. We know it's starting from rest. This is 0 radians per second. Okay. We know this, it was given. So I'll say equals alpha. I'll say given. Okay. We're solving for how much time does it take for that to happen? And we know what speed it has to get up to. It has to get up to this right here. Square root mu g on r. Square root mu g on r. Ooh, you know what? I'm having fun solving this in terms of variables. Maybe I'll just solve in terms of variables. So that can be all right. Right. If you like, you could have plugged in a number. You could have a number at this point. You could have a number right here because you know mu and you know g and you know r. You just pop. Right, pop it in. Right. Oh, I should tell you guys. Remember, guys, don't miss this. They give you radius in what unit? What unit they give you the radius? Centimeters. Can you just take that number and plug it right in here? No, you have to do what to that number first? Exactly. Yeah, convert it to meters by dividing by 100, right? So 15 centimeters, is that 0.15 meters? And that's the number that you would feed right in here, right? Okay. All right. Okay, so it looks like the variables at play, like what we know and what we want to know, is everything except for the angular displacement. Where's a posters? Everything except for angular displacement. Okay, which looks like a job for which one of these guys? First, second, or third? Definitely the second one. Yeah, definitely the second one, right? Because we know that starts from rest is just zeros, whatever that goes away. They told you angular acceleration. We're solving for time, and we went through all that dynamics with centripetal force, blah, 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 the friction, right? To solve for what is omega. that it has to build up to so that the coin slips, right? And we found like a whole square root expression for that. Right, guys, that? Yeah, so it's definitely going to be that second one. Let's go omega that builds up to is omega naught, which is just 0 anyway, plus alpha, which was given, times t that we're solving for. Right? This is root mu times g on r. Okay, so that equals alpha times t. If you're solving for t, last algebra step is just divide by alpha, right? So the time it takes for the coin to start slipping is square root mu times g all divided by r, and then that whole expression divided by alpha. There you go. Here's your general solution. Okay. Now if you like program some computer program, or, like you guys know that's how I make all your quizzes, right? When you guys get 10 different quizzes that are floating around, I'll just solve everything like this. I'll say like, take that cell times that cell, divide by that cell, take the square root, and then divide by that cell, and then pop, 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 and then I get 10 different versions, right? Right? Now you can do it too. Right, you guys get there? Right. Right, so part 1, part 2. Part 1 was solve for how fast does it rotate in radians per second to start slipping, and part 2 was jump back to kinematic motion to figure out how much time does that take. Right? Meanwhile, I could have also asked, I could have said how many rotations does it go through, right? No, if you solve that theta, what unit does it naturally solve in terms of? Not degrees, not revolutions, but radians, right? So suppose you got a number like I'm just gonna make some up, like 20 radians or something, right? Right. But they asked maybe how many revolutions was that? Could you convert from radians to revolutions by doing what? Divided by 2 pi. Exactly. Yeah, divided by 2 pi. Okay. So that's if they ask something like that. Okay. Number 27. Ooh, an air puck of mass so many kilograms is tied to a string and allowed to revolve in a circle on a frictionless table. Okay, so we got like an air hockey table, right? And somebody drilled a hole in the middle and put a string through it, and it's hanging this weight down here. They give you the hanging mass, right? But do you care about this hanging mass, or do you care about the hanging weight? Probably more like the weight, right? And then the suspended mass remains in equilibrium. Now that M2 is in true static equilibrium because it's not even moving. Okay? While the puck and the tabletop revolves around. Oh, this is your guys' lab, isn't it? Right? Isn't this just PVC pipe, string, Play-Doh canisters? That was your guys' lab, right? What is the tension in the string? And what's the horizontal force acting on the puck? And then what's the speed of the puck, right? Right. So let's do that. 27. Yeah, this is totally your guys' lab right here. So you got circular path, string, hole in the table, and then we got like some M2 down here. Plus guy M2, plus guy M1. Right? It's moving at some speed. They asked what's the speed of the puck. I think that implies linear speed, so I'll just go ahead and call it v. Right? Your guys' lab, you guys do that too, right? Okay. So now that's a linear speed. You can also call it tangential velocity. Okay, right. I was reading your guys' lab write-ups. So if you just call it velocity, it's like, well, it's not a constant velocity because the direction's changing. So you can either call it tangential velocity or you can call it speed. Right? Oh, and they also gave you this this radius r, didn't they? I think they gave you r. Yeah, they gave you radius r. Okay. So first question, what's the tension in the string? Let's call it F sub t. The tension force equals, right? Oh, well, can we get that just from the one that's hanging? Let's do a free body diagram on the one that's hanging. It's free body diagram. What's one force on this guy? It's weight. Here's your M2G right there. What's the other force? The tension. And if it's in equilibrium, what is the tension compared to the weight? It's the same, right? Now, really the setup for that would be, the previous step that would lead into that would be the sum of the forces in the y direction is 0 newtons. Therefore, the tension force up minus the M2G down goes to 0. Therefore, and then lead straight to the answer, right? if this was an FRQ, you'd want to write out that step and then that step and then that step. Okay. All right. Next question. Question B. What is the horizontal force acting on the puck? Oh, guys, what is the horizontal force up here? It would be the tension, wouldn't it? All right, so it would just be equivalent to this. So it would just say F sub T or the tension force. Guess what we do it, right? So that's the force acting on this guy. Okay. There's F sub T pulling this way. F sub T. Right. Now, your guys' lab, that was kind of as much what was going on. I had you guys ignore the fact that this swinging mass also had a weight, right? But it didn't really change the answer a whole lot. It may have changed it by like 2%, right? But really, there's now a puck on a table also has its own weight and a normal force acting on it, but there's no friction, so do something like that. But these two go away anyway. Okay. So third question, what's the speed of the puck? Well, here's where you guys get to apply your lab answer. Centripetal force is m v squared over r. Guys, which m is this? Is this m1 or m2? M1, yeah, because it's one on the curved path, right? Centripetal force is equivalent to what was provided by the tension, and that is equivalent to the weight. So can I make that substitution right here? Say m2g equals m1 v squared on r, right? And since the question was, what's the speed of the puck? Oh, well, can you just rearrange that algebraically? You know, we got 2 minutes left, and I got a little space over here. So I'm just going to write the answer in space over here. Right? This is like a continuation, right? Okay. Well, you just multiply by r, divide down the m, take the square root, boom, boom, boom. Those 3 algebra steps. Okay. So v equals so the speed. That's what v is, the speed, right? It's going like kind of into the page. I shouldn't have drawn that like it looks like a force vector. I didn't mean to do that. Maybe I'll make like a fat arrow, make it v, right? Okay, so I got m2g over here, m2g. I'm going to cross multiply the r. I'm going to divide down the m1. And I'm going to take the square root. And that's the answer. Okay. But let's see if this makes sense. So the heavier that m2 is, would this have to go faster? Yeah, that's what the math says, and that also makes intuitive sense, doesn't it? The heavier m2 is, the faster it has to go. What about the more massive m1 is? When you guys did your lab, if you made m1 more and more massive, how do you have to spin it? Slower and slower? Some kind of inverse relationship going on there, right? That matches your lab data too, right? What if we were on a planet that has really strong gravity? It's so strong gravity, you have to spin it how? Really fast or slow? Really fast. Oh, hey, look, that's also in the math, right? Okay, and then some idea with the radial size. How about this? If you speed it faster and faster, is the radial size going to naturally grow longer? Yeah, maybe it's easier thinking of it that way, right? That's also there too. So all that's embedded in that expression right there. All right, here's our pause point today. Pause point.